Now let's consider another further things about this. And one of the students have asked me why I select 10 here rather than other values. Before that, I have to change back to the simulated model first. And now I want to draw this part. Modify the objective function back to the original one. Let's do the M here. And solve the problem again. This initial value is a bad one. So maybe I have to change it. So what's wrong with it? Should I use the correct one? So I have to run that again. So this one is better. So I still use the ITA criterion. You see the step response is lower than IIC criterion, but it settles down on the steady state value fast. And now let's observe the ITAE integral signal. This is the ITAE integral, and the thing is go flat here. Even if you increase the size, you may increase interval as you go flat like this, because the error tends to 0 already. So the curve will be something like this. The ITAE criterion. Goes flat like this. And you can select this one, I think it is 8. So you select 10 or select 20. It doesn't matter. So this one is not quite important unless you select a time like this here. It will cause problems. And after design you can check this curve and see whether it goes flat or not. If it is not going flat, then you have increased the size of this interval. If it goes flat, then which number you choose will not affect to the controllers. Well, it should be noted that if I used a large TF value, here I use a large TF value to 200 or something, then the weighting at the initial time period will be ignored. So the system response may be something like this. So our policy is do not use too large TF values, otherwise the initial response will be neglected. So just use moderate one. Even this one, when the curve goes flat, we can choose one time of the value here, two times, makes 16 or something like that. We do not have to use too large values of TF here.
Why this one will be not?
Because the weighting is T. The weighting is something like this. For small value of T, the weighting is very small. So even if there are oscillations here, it will be ignored. that will be accepted. So we cannot use too much of the interval. We should not use too large value. We should only use a moderate one. This can be checked later on once you design the controller and you can draw the IDA curve and see whether it goes flat or not. If it doesn't, then you have to change value here. So this is the reason why I have to use finite time here. And also, if we want to introduce actuator saturation in the system, we can still use this kind of optimization technique. Because in control, normally, if you do not use a saturation, then the initial error jump is very large. This one is changed to 1 and the output is still 0. So the initial value of the error will be something like this. And here we use a pure derivative, or even you use a first order term, it will generate a very large number in the signal. Maybe we have 1,000, 2,000 or something, or even higher. If it is a real system, then the hardware will be turned out. So normally in control, we have to use actuator saturation here to limit the input to the plant to, for example, 3 volts or something like that. So we can use a saturation. So that as we use infinity here and run simulation here. That's strange. Now understand why. The signal here will be Australian. That's strange. That's strange. So I ran this program earlier. I think the signal should be something like this. Very big jump there, and then settle down.
So that's not the error. You're looking at the optical signal.
Yes, I should observe this point. Anyway, there should be actuator saturation there. So we can add saturations there, and then we can perform optimization. We should gain consistent results. And the demonstration is so in this way. No matter how complicated the system, we can use this way to optimize the parameters. And based on this idea, I've designed an interface called OCD, stands for Optimum Controller Designer.